Others, kindly log in. Okay, I will start. What we discussed now, it was related to geometry. Now let us come to the material thing. We know that from Hooke's law, you know, from Hooke's law for homogeneous linear isotropic material, we wrote for when it is subject to axial loading, sigma is equal to n smallest times epsilon. On the same lines, we can write tau is equal to g times gamma. Shear stress is directly proportional to shear strain within proportional limit. Now, in our case, we are talking about maximum shear stress, which is what we got it. We got here tau is equal to, if I write g into gamma max, maximum shear stress g into gamma max. If I consider maximum shear stress, then it has to be with respect to the maximum shear stress. Okay. Now, now I can also write uh, in any intermediate layer, I can also write tau is equal to g into gamma. This is at the maximum radius, say r. Tau is equal to g times r. Some radius rho, some radius. Give me a moment. Okay. So from Moore's law, I can write lot of disturbances in phase class. From Hooke's law, I can write sigma is equal to n small times epsilon. On the same lines, I can write tau is equal to g times gamma. For maximum shear stress, it should be the maximum shear strain happening at the outermost fiber. For any other radius, tau is equal to d times gamma. Okay. Now, if I write tau is equal to g times gamma, can I write like this? Uh, what we got gamma as? Gamma we got it as rho times gamma max by r. Gamma which is equal to, if I call this as 1, if I call this as 1, okay, 1, gamma is equal to rho times gamma max by r. Gamma which is equal to rho times gamma max by r. Similarly, I can write tau is equal to g into rho into gamma max by r, right? Tau is equal to g into gamma max by r. But what is gamma max? Gamma max, where it is gamma max, is equal to, what is that? We will take from this expression. I can write gamma max from here as, which is equal to tau max by g. Therefore, tau, which is equal to g into rho into tau max tau max by G into R gamma rho, okay, or tau is equal to rho into tau max by R. Okay, as similar to your gamma is equal to rho into gamma max by R. This is also similar to x into gamma max by R, which is varying linearly, which is also equal to shear stress tau is equal to x into tau max by R. This is some function. So this I will call it as 2. When rho is equal to 0, tau is equal to 0 into. When rho is equal to R, tau is equal to tau max into. So how I written the Shasta distribution, if you remember, it is like this, like this, like this, and like this. If I take a shaft, Shasta distribution on the element will be like this, like this, like this, like this. So if we plot this, if you plot this, this is how the Shasta distribution will be. I will take the surface as circus. It is uniform throughout along the length also. The same thing holds good. Due to complementary shear stress theory, if this is like this and the opposite face like this, if you take a section also, the same shear stress will be there. Okay. Now if you take this on the left hand face, okay. Uh, on the left hand face, on this face, this is like this. This is zero at the origin. If I take only this from this radius, this is maximum or this is maximum at the outer shear stress. It is a linear distribution. Maximum at the outer fiber tau max, and then it decreases, 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 and becomes zero. Similarly, when it comes here, this is in this direction. This is tau max decreases, 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 and becomes zero. If I take in this direction, if I take here, if I take here, this is tau. If I write like this, tau become tau become tau max in the same direction, like this, like this. If I take like this will be like this, like this. Same direction as that of your shear stress. This is maximum at outer fiber, zero at the innermost fiber or at the origin. Okay, that you should remember. Next, the torsion formula. Now we'll consider the suction. We'll consider a small in radius. Now we'll consider small area dA. This is small area dA, and you can see, it is subjected to shear stress. Anywhere it is subjected to some shear stress, I will call this as tau. This is subject, like this area is subjected to shear stress tau. Okay, this is the area. This is subjected to shear stress tau. Throughout the length, the shear stress will be induced, and I'm considering only small area for study. Okay, let me give the definition so that so if we know that before that we know that shear stress is equal to tau is equal to F by A, or tau into A is equal to F. Tau into A is equal to F. Okay, if this is the radius, if this is the maximum radius, if this is some other radius other than the maximum radius, so this is rho, I can write tau is equal to A into F. Since I am considering small elemental area, tau into dA is equal to dF. Okay. Now, the shear stress, I will explain this. The shear stress creates a moment about point O, point O, and the resultant of all these moments about point O is equal to applied torque T. The shear stress creates a moment due to the shear stress tau which is acting like this, which creates a moment about point O. What is the shear stress? There is tau into dA into radius rho is the shear stress, which creates a moment about point O. Let me write that moment as dm. Okay, tau into d into rho is equal to dm. If I consider summation of all the moments created by this shear force, this summation of dm will give the summation of this thing will give the torque T. Summation of this dm will give torque T. If I consider all, if I sum all the moments due to the shear forces, shear stresses, in other words, shear forces, then this dm this will give torque T. Okay, then I can write this as dm which is equal to tau into dA into rho. Okay. Now I'll replace what I got tau as tau we expressed as rho into tau max by r from 2 dm is equal to rho into rho into tau max by r. This is rho square tau max by rho square tau max by r into dA, right? Rho square tau max by r into dA. Okay. Now if I integrate this dm, integrate to get the total torque, rho integration to, throughout the area, rho square tau max by r into dA. Integration of this entire moment acting on this cross section will give torque T, which is equal to tau max by r is constant. Integration of A rho square dA. See, rho square dA, there are two types of moment of inertia. For example, you might have been seen if I consider rectangular cross section like this. This is x, this is y axis. This about this axis, if you take the moment, if you take this, if I consider this, I can take the moment of inertia about this axis, this is x axis and y axis. So this is ixx about x axis and iyyy about y axis. If I take the moment of inertia about this point O, as in this case like this, in taking the moment of inertia rho into this shear stress about this point O I'm taking. So this will become polar moment of inertia, which is the sum of these two Cartesian moment of inertia. Izz is equal to Ixx plus Iyy. Therefore, I can write T is equal to tau max, which is nothing but Izz, or I generally indicate polar moment of inertia by J. If this is not Cartesian moment of inertia, it is not about axis, it is about the Z axis, which is the sum of these two axes. Therefore, I will write tau max by R into J. Okay. Now, after saying this, uh, I can write, I can write, we know that what we have written here, tau max is equal to G into gamma max, or I can write gamma max which we got, what we got, R into theta, gamma max we got R into theta. Let me write tau max tau max, which is equal to G into gamma max. A tau max is equal to G into R theta. Okay. Now, now for a bar in pure torsion, for a bar into pure torsion, to note this, theta, the rate of twist, the rate of theta is the rate of twist phi total angle of twist. For example, your friend is holding your towel at one end and you are twisting the towel at the other end. Where is the maximum twist? Your friend is holding at the left end, you are twisting at the right end. So the maximum twist is at the right end. So phi, this rate of twist is theta. Phi is the total angle of twist. Total angle of twist. For pure torsion, this theta, which was actually d phi by dx, now changes to for d phi by dx. For pure torsion, rate of change of theta was, now theta becomes equal to pi by L. Torque remains the same throughout the cross section. This theta, which was d phi by dx, becomes equal to pi by L. Okay. Now let me write. Let me write. This was the expression. T, what we got? Uh, theta is equal to pi by L. Okay. Okay. I'll take this expression. Tau max is equal to gr theta. Tau max is equal to gr. It's very simple. Don't worry. Since I'm doing it for the first time, it's feeling a little strange. This is, we can directly substitute tau max equal to gr theta. At tau max, we got theta. I can write like this: T into R by J. Tau max, I can write T into R by J. T R by J is equal to gr theta. Okay, gr theta. Or T by J is equal to g theta. Theta is equal to pi by L. This I will call it as 4. From 4, T by J is equal to G into pi by L. Okay. We also derived T by J. T by J is equal to tau max by R. Or I can write T by J, which is equal to tau max or tau by R, which is equal to G pi by L. This is the derivation for your torsion equation. This is the derivation. T by J is equal to tau by R is equal to G. Some authors with the G theta only. But this theta, when it talks about theta, it is the rate of twist. For pure torsion, it is theta is equal to pi by L, where pi is the total angle of twist. I am expressing it as pi, G pi by L. Okay, theta is tau by J, T by J is equal to tau by R is equal to G pi by L. Okay, any doubts here? This is very important. Conceptually, you should understand this. Any doubts up to here? Any doubts? Any doubts? Any doubts?
No, sir.
Okay. Now we will discuss few more parameters in the next class. What is torsional strength? What is torsional rigidity? Okay. What is polar suction modulus? What is mental strength criteria? Rigidity criteria? We will discuss. We will take one more class for that. And problems are take it from me. Take it from me. These problems are very easy. So you can directly substitute the formula and you can get the answers. Okay, I'll stop at this point. Any doubts you can call me or approach me. In the afternoon, 2 o'clock, we'll be conducting the experiment. Renal, Rockwell, and Isolan chapter test will complete. The instructor has come today. We'll try to complete it. So let me confirm you. I'll call and confirm you. We'll put a message. He said, yesterday I called him, I spoke with him. He said he will be coming, but I am not seeing in the morning. Give me 2 minutes time. I'll confirm it. Okay. Shall I stop at this point?
Yes, sir.